Alright, so what I want to do in this video is work through a number of problems using the fundamental theorem of calculus part 1. So recall that what the FTC part 1 is saying is that the derivative of the definite integral from a to x of f of t is equal to the function itself, but as a function of x, f of x. Now one thing that's very important to note here is that I'm using different symbol for the x here, the endpoint, and the variable t over which I am integrating. So you cannot use, for example, x in both cases. That would be wrong because you would use the same symbol to denote different things. T is the dummy variable over which I'm integrating, while x here is the endpoint of the integral. Okay, so let's see how we can use that in concrete problems. So if I ask you, for example, to evaluate the derivative of this definite integral, then you can use FTC directly to write the answer. You know that the answer is just going to be the function inside, but as a function of x. So this is what I would get by FTC. And that's it. So it's a very fast way of evaluating this kind of expression. Now, just for fun, let's do it the old-fashioned way. So what we could also do in this case is just evaluate the integral first. So that expression would be the derivative of the integral here. Now, if you look back at your table of integral, you will realize that the integral of this function is just the inverse hyperbolic sine function. And now, of course, this is between 2 and x. So what I end up with here is the derivative of the inverse hyperbolic sine function minus the derivative of the inverse hyperbolic sine evaluated at 2, which is just a constant, so I get 0 when I take the derivative. And looking back at your table again, you see that the derivative of the inverse hyperbolic sine is just 1 over square root of 1 plus x squared, which is indeed the same answer that we had obtained previously. So it works, but this was a very inefficient way of doing it. FTC enabled us to bypass the step of integrating and just write the answer directly. Now I should mention, and that will be the case in the next example, that sometimes there's no other way of doing it. You cannot always do the long way, because sometimes you cannot write down explicitly an antiderivative for a given function. And in fact, it happens pretty often, surprisingly. If I write this expression, for example, if you were trying to first evaluate the integral of this function, you would not be able to write an explicit antiderivative. This is what we call an elliptic integral. Even though it looks pretty simple, it's not that simple. You cannot write down the antiderivative. So the only way you can evaluate this expression directly is using the FTC. Now in this case, using the FTC is very easy. The derivative here of this definite integral is just the function inside, but as a function of x. So this is what the result will be by fundamental theorem of calculus. No need to integrate. Okay, so these are cool. Sometimes it's a little more complicated. So let's go through two more examples that involve a few more steps. So here's the next one. So I'm asking you to evaluate the derivative of the exact same integral, but note that I've exchanged the endpoints. Instead of integrating from 0 to x, I'm integrating from x to 0. I cannot use FTC directly here, because FTC was for x when x was the upper limit of integration. But what I can do is exchange the limits of integrations. I know that the integral from x to 0 is equal to minus the integral from 0 to x. So I can rewrite that as minus d dx of the integral from 0 to x of the same expression. And now I can use FTC to evaluate this integral here. By FTC, this is just the function inside. Still have my minus sign, and then I get the function inside, but as a function of x. And that would be the final answer by FTC. So there was one more step here, which was the exchange of the limits of integration. Okay, but sometimes it's even more complicated than that. All right, so let's look at the next example. I'm asking you to evaluate the derivative of the integral of sine of t between pi and x squared. How can I do that? I can't use the FTC directly because the upper limit of integration is not x. The upper limit of integration here is itself a function of x, it's x squared. So in other words, this thing here is a function of x. So what do I do when I want to evaluate the derivative of a function of x? I use the chain rule. So let's do that explicitly. So what I'll do is define the function u is equal to x squared. To make it explicit, this becomes now d dx of the integral between pi and u of x of sine of t dt. This is a function of a function, so I'm using the chain rule. First find the derivative of the outer function, so this is d du of the integral between pi and u of sine of t dt times the derivative of the inner function, which is du dx. All right, and now I can use the FTC to evaluate the first part. Now this becomes just by FTC, becomes just a function inside evaluated at u, sine of u. Now du dx, remember, recall that u is equal to x squared, so du dx will be 2x. And that's not quite the final answer because I need to rewrite everything in terms of x. U is equal to x squared, so what I get is 2x sine of x squared for the final answer. So the key in this example was to combine FTC with a chain rule, which is something you may have to do in a number of examples. All right, so let me leave you with a more complicated example. I'm not going to do it here. I'll leave that as an exercise. So if I ask you to evaluate the derivative of the integral of 1 plus t squared between sine of x and cos of x, how would you do that? I'll leave that as an exercise. Think about it. Try it yourself. You should be able to do it using FTC and chain rule. And we'll try it and we'll come back to it in class.